Hi guys, this is Mrs. Allison. We are starting our next unit, which is a radical unit. It's called radicals. So I should probably define what a radical is so you know. A radical is the same thing, you may hear it called roots. And it all deals with this symbol that I just wrote, otherwise known as a square root when it's written like this. But this root, as you move further on in math, can have different what we call indices or indexes. Plural for index is indices. And that's the little number that goes right here. So you could see cube root, which is a little 3 in the index. You could see a fourth root. You could see all the way up to whatever number you would like to put in there. Now, this is called a square root because even though it's not written, it is implied that in the index is a 2. So it's never written. We don't write that index of a 2, but it's implied. That's why it's called a square root, because it deals with squares. Okay? Okay. To go forward, the first thing that we're going to do is talk about what's called the product property of square roots. It often actually just says the product property of radicals or the product property of roots. We've dealt with product properties before. Do you remember? We did the zero product property when we were talking about solving quadratics. Well, this is not the zero product property. This is just product property. And what does product mean? Right, it's the answer to a multiplication problem. So this is the product property of square roots. And here's what it says. It says that if we have any square root of AB, which written this way, even though it's not there, implies that there is a multiplication sign in between the A and the B. The product of the square root of A times B is equal to the square root of A times the square root of B. So it doesn't matter if they're multiplied inside, we can separate the square roots on the outside. So that's the product property of square roots, and we're going to use that going forward to separate some of our problems. Okay, there are actually two methods to be able to simplify radicals, okay? And when we talk about simplifying radicals, the answer is called simplified radical form or exact, and we'll go talk about that in just a minute. There are two methods, and really it kind of depends on which method you like better. I can tell you the one that I think is a little bit more straightforward is this first method. That doesn't mean you have to use it, and there are situations where method 2 works better. But the first method is called perfect squares, and here's how we do this. The first thing that we're going to do is we are going to find the largest perfect square, and we'll define what a perfect square here is in just a minute. Largest perfect square factor. So we're going to find the largest perfect square factor. And remember, a factor means it's something that multiplies into the number. So like, for example, our factors of 6 are 2 and 3. Okay? Or 1 and 6. If we're looking for the largest perfect square factor, we're looking for something a little bit different. So let's talk about our perfect squares. How many of you know what a perfect square is? Well, a perfect square is a number that we can take the square root of. It is a number that is multiplied by 2 of the exact same other numbers to get it. So for example, 1 is a perfect square because 1 times 1 is 1. Okay, I'm going to write 1 times 1 so you can see it. 4 is a perfect square because 2 times 2 is 4. 9 is a perfect square because 3 times 3 is 9. 16 is a perfect square because 4 times 4 is 16. And 25 is a perfect square because 5 times 5 gives me 25. Do you get the idea? So my perfect squares, 36, 49, up to 7, we could keep going, ideally. Ideally, you know your perfect squares all the way up to at least 100, maybe even 400. So 49 would be 7, 8 would be 64, because 8 times 8 is 64, 81, 100. At the very minimum, you should know those. Okay. Chances are, if we're looking for a perfect square factor, something that goes into it, one of these is going to be sufficient. Okay. So my second step in using the method of perfect squares is we are going to use the product property. So meaning we are going to separate our radicals, or we're going to separate our radical into two radicals. Use the product property. And the third thing is to simplify. Okay, so let's look at some examples of this. Okay, so here we have an example where we're doing the square root of 72. And I'm actually going to do this two different ways. I'm going to do it the way we just looked at, the method one. And I'm going to tweak method one just a little bit because 72 allows me to do that. And I'll show you why. Okay. If we're going to find our largest perfect square, let's just write our perfect squares up here. So 1, 4, why did it stop writing? 1, 4, 9, 16, 25, 36, 49, 7, 8, 64, 81, 100. So these are my perfect squares. Which of these is the largest number that can go into 72, or that is a factor of 72? Okay, well, obviously 100 is not it because it's too big. So let's start with the next biggest one, 64. Well, 64 doesn't go into 72 evenly. 49 doesn't go into 72 evenly, but 36 does. So if I rewrite 72, do you agree I could rewrite 72 as being 36 times 2? Okay. So this is my largest perfect square, is 36 factors that go into 72. And now I'm going to use the product property, which says that if it's written as one radical like this, radical is another name for root, I can rewrite it to be the square root of 36 times the square root of 2, and that says the exact same thing. Okay, so if I do it this way, tell me why I would do this. What do we know about the square root of 36? This is why we looked for perfect squares. Right, the square root of 36 is 6, but I don't know the square root of 2, so it stays. Okay, so my final answer is 6 root 2. Okay, 6 root 2. This is what we call simplified radical form. So I'm going to write that down. Simplified radical form. This is going to become really big next year in geometry. You're going to use simplified radical form a lot. Or if it asks for an exact answer. If it asks for an exact answer, I want to use 6 root 2. The reason is if I type 6 square root of 2 in my calculator, I get something like 8.485281374. So anytime I shorten that decimal by any amount, I've changed the problem. I've rounded it. So it's no longer an exact number, it's an approximation of what we think it is. Okay, I would love it if you would try right now to pause the video and just see how you do with the square root of 20. See if you can go through this process to get the simplified radical form for the square root of 20. Okay, hopefully you've gone through and had a chance to look at the square root of 20. And if we do that, I'm going to start all the way down here. I know 16 does not go into 20, 9 doesn't go into 20, 4 does. So I can rewrite the square root of 20 as the square root of 4 times 5. Then using my product property, that gives me the square root of 4 times the square root of 5. And the square root of 4 we know is 2. So my simplified radical form is 2 root 5. How'd you do? Okay, so try the next one. See how you do. Pause the video and come back. Okay, so hopefully you've had a chance to go through the square root of 48. So let's go through the process that I go through one more time. I know 48, I'm looking for perfect squares. Well, 49 is too big, so 36. Does 36 go into 48? No. Does 25 go into 48? No. Does 16 go into 48? Yes. 16 does go into 48. And I know that 16 times 3 is equivalent to the square root of 48. So using my product property, I can separate this to be the square root of 16 times the square root of 3, which means I get 4 root 3. And there's my final answer. How'd you do? Okay. Now, let's go on to method 2. Most of the time, oops, I went backwards. I did not mean to do that. Hold on. Okay, so method 2 is a useful method if, for some reason, you cannot think of a perfect square that goes into your number, or you're just hung up on it and you just need to start working on it. The pair method works. This method would change names the higher the roots we go. So for example, we're dealing with square roots, which is why we're talking about pairs. If you were dealing with cube roots, you would talk about triples. Fourth roots, you'd talk about quadruples, so 4 of a kind. But here we're just talking about pairs because we're dealing with square root. Okay, so this is what we would do to use the pair method. The first thing we would do is we would break our radicand. That's that number underneath the radical. I'll write that down. We would break our radicand. This is the number under the root. What happened there? That was real weird. It put me in a draw mode. Okay, hold on. The number under the square root. Okay, so we would break the radicand into its prime factors. Okay, so that's just figuring out what we sometimes call this. This process is sometimes called prime factorization. So you may have heard that phrase before. Factorization. It's looking for, ran out of room, it's looking for all of the smallest prime numbers that multiply to give us that number. Okay, so break radicand into the prime factors. What we're then going to do is we are going to group the pairs of the same numbers. 2 of a kind is what we're looking for. Pairs of same numbers. And then what we're going to do is we are going to simplify. Now this requires a little bit more steps involved. That's the basic steps. But what I want you to remember is we are going to multiply outside by outside. And I don't have room to write it, but we're going to multiply inside by inside. And you'll see what I mean by this in just a second. Okay, so let's look at an example of a problem. Square root of 72, it's the exact same problem we did first on that last page, on the last set of examples. It's the same one, so we should end up with 6 root 2. So let's look at how this works. Okay, so a prime factorization looks like this. Some people draw factor trees if that helps you to organize it. Some don't. Some just write their prime factorization. So for example, 2 and 36. You know what? Let's pretend we couldn't think of 2 and 36 because those are perfect squares. So, or 36 is a perfect square. Let's say we knew 72 is 8 times 9. And do you agree that 8 is 4 times 2 and 9 is 3 times 3? And then do you agree 4 is 2 times 2? So the prime factorization, or the prime factors that I have, are 2, 2, 2, 3, 3. So those come from the 2 here, 2 here, 2 here, 3 here, 3 here. Go ahead and check my math. If you check my math and do 2 times 2 times 2 times 3 times 3, 2 times 2 is 4, times 2 is 8, times 3 is 24, times 3 is 72. This is what we call the prime factorization. Every one of these numbers is prime, and it's all the numbers that it needs to multiply back to 72. Now, by grouping pairs of the same number, now I'm going to re-multiply, and this step you maybe could skip, but I'm going to re-multiply some of them. So I'm going to re-multiply the 2 2's here to give me 4. I'm going to re-multiply the 2 3's here to give me 9. And then I still have that 2 that didn't have a pair to multiply by. Now using the product property, I have the square root of 4 times the square root of 2 times the square root of 9. Well, what do we know about the square root of 4? It's 2. We don't know anything about the square root of 2, but we do know the square root of 9 is 3. I don't know why my 3's are not looking like 3's. There we go. Now, when I said to simplify and multiply outside by outside, inside by inside, means that if I have numbers that are not in a square root anymore, like this 3 or this 2, when I multiply, I can multiply those because they're outside of the square root. And what do those multiply to? Well, they multiply 2 times 3 is 6. And there's nothing left inside to multiply other than the root 2 that's already there. So my final answer is 6 root 2. Okay, here is why I like method 1. Did method 2 get us the answer? Yeah, sure did. But how much more work was it? So much more work. So in my opinion, if you can find a perfect square, you're better off. Okay, but I would like you to try method 2, hit pause, try method 2 and see how you do on the square root of 48. Okay, so hopefully you had a chance to try this. And if we look at 48, let's do 6 and 8 because we know those multiply. 6 and 8 is 3 and 2, and 8 is 4 and 2, which means 4 is 2 and 2. So my prime factorization would be 3 times 2 times 2 times 2 times 2. Let's make sure we got that. 3 times 2 times 2 times 2 times 2. So I should have 4 2's and 1 3. Okay, so if I rewrite this square root here as 4, and this square root, or those 2 times as 4, so I have root 3 times 4 times 4. Using the product property, I can say root 3 times root 4 times root 4, and we know the square root of 4 is 3, root 3 times 2 times 2, normal numbers. Now we typically write normal numbers in front, so we would do 4 root 3. And what do you notice about this answer as compared to the one where you did it using the perfect squares? They should be the same. Okay. So that's the pair method. You get to choose which one you use, but you will see most of the time I'm probably going to use perfect squares method. I just like it a little bit better. So let's move on. Let's make it a little more fun, shall we? Okay. So what do you think happens if there's a number in front, like this 8 or this -3? Do you think that affects anything? Well, it actually doesn't affect a whole lot. What it does is it will change our final answer, and we'll see that in just a second. But basically, I worry about the radical, the square root, and kind of ignore the 8 to begin with. It plays a part in the end. So try simplifying the square root of 8 for me using whichever method you'd like. Okay, hopefully you had a chance to try this. I'm going to go just a little bit quicker on this part. Using perfect squares method, I'm going to ignore the 8 that was out front. I am going to multiply 4 times 2. I know what the square root of 4 is, so I'm going to separate my radicals using the product property. And then I know what the square root of 4 is, And that's 2. And we have this 8. Now, what operation do you think is happening between the 8 and the 2? If you guess multiplication, you're correct. Remember in the last problem, method 2, we said if you're simplifying, you multiply outside by outside and multiply inside by inside. Well, my 2 outsides are 8 and 2, so I have 16 root 2 is my final answer. If you were to type in your calculator 8 root 8 and get the decimal, and 16 root 2 and get the decimal, you would see they are the same decimals. However, 16 root 2 has been simplified completely, whereas 8 root 8 has not. Okay, so try the next one and see how you do. Okay, hopefully you've had a chance to try the next one. So let's go through that. So I have -3 square root of 25 times 3 using my perfect squares method. This does say 25 despite whatever number that looked like. Okay, we know the square root of 25 is 5. That's going to get multiplied by the -3, so I get -15 root 3. How'd you do? All right, well, let's make it just a little more fun. So what do you think is going to happen when we deal with variables? What about variables? You know, the algebra part. Okay. Why did we use the perfect square method up above? Like, why did we get it so that it was the square root of 4? It's because we know the square root of 4, right? Because 4 is a perfect square. 25, in the second problem over there, is the perfect square. So why? Why is that important? Well, because I know the value of that. I know it can simplify. I don't know anything about square root of 3, so I can't simplify it. But I do know the perfect squares. So what do you notice about x squared? Hopefully what you noticed is that x squared is a perfect square. Okay, so since it's a perfect square, I know that the square root of x squared is just x. Okay, so how does that help me? Okay, so if I have the square root of x cubed, I'm going to rewrite it. I'm going to find the largest perfect square factor that goes into it, and that's x squared. And x squared times x is the same thing as x cubed. Do you agree? Well, now I can use the product property and I get x squared and x. And the square root of x squared is x, and the square root of x is just square root of x. So my final answer is x root x. How'd you do? Okay, what about x to the 4th? What do you think? Hopefully what you think is that x to the 4th is the same thing as x squared times x squared, which is the same thing as the square root of x squared times the square root of x squared, using the product property. And the square root of x squared is x. Square root of x squared is x, and x times x is x squared. X times x is x squared. How'd you do? All right, you ready to make it really fun? Okay, I do not want you to panic because you know how to do these problems, believe it or not. And here's how we're going to do these problems. The first thing I want you to think about is I actually have 3 distinct problems here. I have a root 12, root x squared, and a root y cubed. So I'm going to rewrite this as 3 distinct problems. Square root of 12, square root of x squared, square root of y cubed. Now I'm going to go through whichever method you would prefer. I'm going to do method 1 to simplify. Watch. Square root of 12 is 4 times 3, which is the square root of 4 times the square root of 3, which gives me 2 root 3. Square root of x squared, well, that's just a perfect square already, so it's just x. The square root of y cubed is y squared times y. I'm really struggling with the 2's today. They kind of look like not 2's. Okay, y squared times y, which rewriting using the product method, the product property, I get y squared, square root of y squared, and the square root of y. And I know this is y root y. Okay, so I kind of have a jumble of a mess here. I've got a 2 root 3, I've got an x, I've got a y root y. Well, remember back in method 2 when we talked about multiply the outside by outside and the inside by inside? Here we go. The numbers that are outside currently are a 2, an x, and a y. 2, no radical, and y, no radical. The numbers that are inside are 3 and y. So my final answer is 2xy root 3y. This is the simplified version of root 12x squared y cubed. Do you see how we took it into 3 parts? Okay, hit pause. Try this last one. Okay, let's see how you did. The first thing I'm going to do is I'm going to write 4 problems this time. Square root of 20, square root of x to the 5th, square root of y squared, square root of z to the 3rd. Now time to simplify. Square root of 20, well, we already know it. We've done it before, but we get 4 times 5, which is the square root of 4, times the square root of 5, which gives me 2 root 5. Using x to the 5th. This one's a little bit messier, but I know x squared. Goodness gracious. The 2's do not want to go for me. 2x squared, x is the same thing as x to the 5th. Do you agree? I have 5 total x's there. So I have the square root of x squared. Goodness. The square root of x squared and the square root of x. Square root of y squared, that's nice, that's just y. And z cubed, we've done, it wasn't z, but we've done it. So z cubed and z, whoops, no it's not. Z squared and z, multiply to give me z cubed. So then with the x's, I can pull out an x and a root x stays in. I have a y. I can pull out a z, and I'm left with a z on the inside. I think I took too many steps there. Okay, now remember I'm going to multiply outside by outside, inside by inside. So I have 2x squared, because there's 2 of them, y, z, and left inside is 5x, z. How'd you do? Okay. If you need to, obviously rewind the video, watch whatever you need to watch again, or email me any questions that you have. We'll see you soon.